CBT Nuggets, JNCIA Series, Junos Routing Essentials. Now, one of the first things you're going to find out when you get to Nugget Lab is that they've already divided up or partitioned their network into different domains or security zones. And those zones are what we would call broadcast domains. And we're looking at things like the pool of corporate endpoints. We've also got a small data center. We have a DMZ where we have our public-facing servers. We also have internet connectivity as well. So with all of those needs and demands in place, it's important or essential that we understand Junos routing. So in this nugget, we're going to cover some routing fundamentals, some things we've already talked about, but we're going to reiterate and then expand on that. We'll look at routing tables and routing instances, very fascinating, especially from a service provider standpoint. We'll compare static routing and dynamic routing. We'll jump into some static routing configuration. We've got some options there. And then, of course, we want to test our connectivity and verify connectivity between our layer 3 devices. Sound good? Let's get to it. Okay, to explore routing a little bit further, let's go back to that diagram we started out with earlier in this Nugget series. If we take a look at my network, which is down here, which has basically one connection to this gateway, and my destination, I'm driving my green car here. It looks a lot like my first car, which was a green Firebird that I had when I was a teenager. And so my destination is to drive to work every day, right? And here's my office, which actually connects to two gateways, okay, for redundancy's sake. Not a very uncommon scenario, as a matter of fact. Now, here's the point about routing. If the packet and the payload is the passenger inside, right? We determined that. That's the payload, that's the data packet, and our automobile with its registration and licensing and all that is the metadata that encapsulates the payload. The goal is to drive that payload in the most efficient and effective manner from point A, which is my home, to point B, which is my office. Now, I have some options. I could take the same path every day, right? I could get in my car, I could drive here, take a right, go down to this gateway, get on the freeway, and then of course drive down, take my first exit, and boom, there I am. And I could tell every one of these gateways or layer 3 devices / routers along the way. I could manually configure the next hop or the path to get to that next prefix or network. And so every day I'm taking the same static or manually configured route that's configured on all these devices. But that introduces some problems and some challenges. Network paths are dynamic. They don't always stay the same way, especially over the internet or over a large campus network. And just like a metropolitan area, sometimes I have more traffic on some links than others. As a matter of fact, I might have a bunch of 18-wheelers taking this path someday. Maybe there's a funeral procession that's coming down this way. Maybe at the Air Force Base out here, we have a bunch of traffic that is sending out equipment and trucks and military personnel. And so from time to time, I may have to modify my path from my home to my office to get there effectively. Now, if I'm using a static or manual method, I have to literally go to each one of these gateways and change the information so I can be rerouted on a different path, okay? And I can still use static routing to do that, but it involves a lot more complexity and in some ways trickery. What we really want to do is we want to let our routers or our gateways figure out the best path for me to take every time I want to go to work. It's the same thing in our enterprise, right? We really want to connect to our upstream service provider, and then we'll use a static route for that. So for example, let's say this is my service provider. I'm going to connect to my upstream service provider with a static route, but my service provider is going to have some very complex metrics and dynamic routing protocols to figure out the best path to move packets across their core network. Now what's interesting is we can see that there's 1, 2, 3, 4, 5, about 5 or 6 routers in between point A and point B. And for most networks, most corporate or enterprise service provider networks, the depth or the number of hops is usually no more than 5 to 7, okay? This is actually pretty realistic and pretty practical. But this could also be in a large campus. Now, Nugget Lab's not a large campus, but eventually we'll be looking at that and deploying that. And since eventually you are going to go from Nugget Lab to some larger, possibly service provider organization or large enterprise, once you've mastered the tasks at hand and you're going to move forward in your career, we want to build that same skill set. Okay, so our basic definition of routing is to move data packets between layer 3 networks, okay? From one layer 3 network to the next layer 3 network, or from one broadcast domain to another broadcast domain. Now, routers are typically the device of choice for performing routing operations. However, we have a lot of switches that have routing processing in them, okay, or what we call a layer 3 switch. My EX2200 also does routing. In other words, you can take that default Ethernet switching interface and quickly make it a routing interface. In addition, our security devices and security appliances will also perform routing. Now, there's two main requirements for moving traffic between layer 3 devices, okay? The first is, do we have end-to-end communications, okay? So we have to have an efficient and reliable end-to-end communication path. So as I can see here, from point A, which is my home, to point B, which is my office, I've got several end-to-end communication paths, and these routers are going to make those possible. And like I mentioned earlier, the ability to be able to move and choose a different path if necessary is one of the most important functions of both static and dynamic routing. So if we have a physical path configured and operating properly, we've met that end-to-end communication, okay? Remember, routing is a layer 3 process that really sits on top of and uses the OSI physical layer 1 and layer 2, which involves different types of encapsulation or framing. Now, the second thing we have to accomplish is making sure that all of our layer 3 devices in our reliable end-to-end communication path have all the information they need, okay? Do they have the necessary information? And that's what I mentioned previously, okay? We can either manually or statically configure that information on all of our devices that are participating in this network domain, or we could rely upon some other dynamic, automatic method. So, this data, this information that we need, what is the main purpose of this information? Well, it's to determine what is the best next hop. So if you take a look at a router like this one, for example, okay, it needs to be able to figure out, is the best next hop go to that router, or that router, or that router? And it's determining the next hop based on the destination prefix. That's the IP address / whatever. And remember, what we're looking for ultimately is the longest match, or the longest prefix, okay? Till eventually we get to the host, which of course has a /32 prefix. Now, if this is a Junos operating system device, which ours are, a couple of ours are, we're not using all Junos devices as we looked at the topology earlier, but if it's running a Junos operating system, it's going to use the forwarding table. Remember? And the forwarding table is a subset, or it's a portion of the information found in the route table, and we use that to make our determination. So with that information under our belt, let's go and explore in greater detail that very important routing table. Okay, on the 2320, I'm going to do a show route command in operational mode. And I'm going to see a bunch of routes here in this INET 0 or INET.0 routing table. Now, this is the IP version 4 unicast traffic routing table. And what I see are entries from the previous configurations of these interfaces. Now, remember, the Junos OS routing table is going to basically consolidate a bunch of prefixes that it learns from routing information sources. And what are those routing information sources? Well, if it's directly connected, that network would be a routing source. It could also be, a locally assigned address to an interface. Okay, that's a routing address source. It could be a static that you've created. For example, here's a static entry I created on gig E000, basically so I can ping my management station. This is my management network. So far I see three sources of information. Direct routes based on local configuration, local addresses on interfaces, and a manually or an administratively added address. Now again, the static route that we see here, this is one that I, as an administrator, manually entered into the router, and I'll show you those commands here in a moment. If there's a topology change somewhere in this environment between these different connections that I've got here, I'll need to go and make a change to my static route. Now the advantage is this is much more secure, and it gives me precise control over the routing behavior of my topology. A dynamic route, which can also add data to this routing table, like OSPF for example, will make adjustments or modifications automatically if there's a change in the traffic or the topology. It'll also dynamically learn and maintain routes to other remote destinations, then exchange that information with this router so I can update my routing table. They also have the ability to discover new networks and then share this information in various ways. Now, this is the INET 0, but there are other routing tables. For example, we know that INET.0 is for IP version 4 unicast traffic. INET.1 is the multicast forwarding cache. We'll learn more about that one when we get deeper into Juniper. INET.2 is used for MBGP, which is the multicast border gateway protocol. INET.3 is multi-protocol label switching, or MPLS, path information. INET.4, this is used for MSDP, the multicast source discovery protocol, those route entries. INET.6 is IPv6 unicast routes, and MPLS.0 is used for our MPLS next hops. And there are others. For example, there's ISO.0, which is the ISIS or ISIS routing table. Now, the ones you need to know for the exam are, of course, INET 0. You have to know that one. I want you to know INET.3, which is the MPLS path info, and INET.6, which is the unicast routes for IPv6. Be careful, okay? Don't get tricked by seeing something like INET v.6 or something like that. That V shouldn't be in there. Okay, we know it's v6 or version 6 for IPv6, but a very clever distractor in an exam question might be something like INET v.6. Let's explore this a little bit more here. We can see that we have this asterisk, which basically tells us that this is the, active route, okay? And the asterisk means both. Technically, the plus is the active route, but we don't have more than one option here. So the asterisk is going to tell us that this has been the selected active route. Now, down here, we're going to see that this is the selected path, okay? The path, the greater than symbol, is going to be via the gig E003 interface unit 0, okay? So that's the method that we take to get to this network, 18.1/30. Direct is the route source, so it's a directly connected or local route or static route, or it could say OSPF, we'll see those here. And then this is what we call the route preference. Now I'm going to talk about route preference a little bit greater detail here in a moment, but just realize that I could have multiple paths to network 172.18.1.0. My Junos INET 0 routing table will allow for that. If that were the case, I would have multiple via entries here. And the way this works is the routing protocol daemon, or the RPD, is going to choose an available path in a pseudo-random fashion. So that way, my Junos router can distribute the load among 2 or 3 or more paths, and also kind of maintain the ordering of packets on a per destination basis. Later on in your Junos knowledge, you'll learn how to do per flow load balancing. I'll show you how to do that. That's beyond the scope of the JNCIA. But just realize I can have multiples, and the path that's chosen would have the greater than symbol in front of it. Now, up here we see, active routes, okay? It says there's 9 active routes, and we can see that because there's 9 asterisks down here. These are all of our active routes. What's a hold down? Well, hold down route. Well, a hold down are routes that are in a certain state. They're in a kind of a pending state, kind of a zombie state, because they're waiting for the Junos operating system to declare them as being inactive for some reason. And we're going to talk about that when we talk about, for example, RIP version 2 in the next nugget. A hidden route, and there are some hidden routes usually on your operating system, these are ones that can't be used. For example, like it's invalid, it has an invalid next hop, for example, or maybe it's got a route policy that's hiding it. We'll talk more about that as well. Now we know that the information in the routing table, a subset or a partitioning of this information is going to be sent to the forwarding table. But before I show you the forwarding table, I do want to talk about this particular value right here. This 5 that we see here and this 0 we see here. This is what we call route preference. It's a very important number. We want to talk about it. Okay, here's a question for you. Let's say you show up at Nugget Lab and you walk in and you look at a particular router's routing table. And that router is a gateway between different types of networks using different dynamic routing protocols. You've got connected networks, you've got static entries. How does your routing table determine what is the preferred route? Because it could be getting information about the same prefix or the same destination network from multiple sources. Well, that's where the preference comes in. So there's a ranking that goes on. And this is like a golf score, right? Not my golf score, but it's like a golf score where the lower number is preferred. And by the way, unlike golf, you don't get any handicapping here, right? So now, could we rig the game? Sure we could. But if you can see here, if we remember from our routing table, I had direct routes and local routes. Those had a default preference of 0, and it doesn't get any better than that. That's the lowest it can be. So those are always going to be preferred over some other method. For example, like a static route, which has a number of 5, or an OSPF, Open Shortest Path First, internal route, which has a number of 10. Then we skip up to RIP. RIP has a route preference of 100. If it's an external route coming from a different area, for example, different OSPF area, then it's going to be 150. BGP 170, and there's others, okay? For example, we'll be learning about protocols like ISIS or ISIS. Depending upon whether that's internal or external, those can have their own preferences. If it's information learned from the operating system, from Junos itself, the kernel, that has a preference of 40, okay? Don't have to memorize these. I'm just telling you that there are others out there. And these are important because this is the information that we use to determine what route has that asterisk next to it, okay? What's going to be the active route. Now, for you Cisco people out there, you may remember this as being something known as AD, or administrative distance, okay? We have the same kind of construct in the Cisco world, and it might be familiar to you. That actually could come into play if you're trying to distribute routing information from a Cisco router to a Juniper router and vice versa. We'll deal with that when we get there. Now here's a question you might ask. If I'm using a network that has OSPF routing and RIP routing, could I take the OSPF AS external and tweak that or modify it so it has a value less than the RIP, okay, which is 100? Could I change it, let's say, to 90? Yes, you could do that. You can make them more desirable or less desirable depending upon your environment. The only exception is you cannot modify a direct route or a local route. You can indeed modify the static route, and that's often done from time to time. Now, if my route table gets pretty large, which it can be in a large enterprise environment, I may only want to show the routes of particular sources. For example, if I only want to see the direct routes, I could say show route protocol direct. It'll just show me those. What if I want to say just show me the static routes? Okay, I can show that, just that one static route that I have that gets me to my management station. I could also say, let's say show route protocol OSPF, and it's going to tell me, guess what? I don't really have any, okay? It's just going to give me that particular entry, INET 0, and the base information. I don't have any OSPF routes. That's also a very handy command. Okay, now I mentioned that the forwarding table is going to store a smaller partitioning of the routing table information, a subset. We can use the forwarding table to locate information that our Junos OS device uses to actually forward packets. Information like the destination prefixes that it's learned, or the outgoing interfaces that are associated with each destination prefix. So I can do a show route and then forwarding. Oops, I need to put more in there. There we go. Show route forwarding table. And we can garner a lot of information from this. Okay, the first thing we see is the output of the forwarding table as derived from the default INET or IP version 4 route table. And again, can we have other INET version 4 routing tables? Sure we could. Okay. Now what we see over here is our destination. This is the first column, destination. Right off the bat, you're going to see this entry known as default. This is important. This is what the Junos operating system or the kernel will add, and it's a permanent one. And you can see here as the type it says permanent. Why do we have this? Well, this is going to match all the packets if there is no other matching entry in this table. So by default, what's going to happen is if there is no entry in the forwarding table that matches a packet, it's going to reject it, RJCT. In other words, it's going to send it to this next hop interface. So the reject interface is basically going to say we want to discard this. This is the bit bucket, or like on Cisco, the null zero interface. When you say reject, you're going to discard it, but you're going to send an ICMP unreachable message. Okay. Now discard is also an interface next hop. The discard, though, will discard, but it'll do it silently. Okay, it won't send any ICMP unreachable message. Now let's focus on this type column here. It's very important. Obviously we have some that are permanent, that are basically installed by the kernel. Then we have INTF. Okay, this is basically here as a result of configuring an interface. For example, 172.18.1.0 or specifically 1.2. And we can see these as, part of these interfaces that I configured on my J2320. You've also got DEST. This means it's a remote address that you can reach directly through an interface. So usually when we configure an interface IP address, we're going to have an interface type and a destination type that says you get to that network through this interface. And this, of course, over here has, this is the next hop. If I hit the space bar, I can go down and see, for example, there's a default ISO table. We really just want to focus on this one right here, though. Now, there's some other common next hop types that we see over here, because this has the next hop address or network and the type. We've already mentioned reject and discard. There's also local, and that's basically the local address on an interface, whether it's a loopback or an interface like 1.2. RECV means receive interface. BCST, broadcast. So this is obviously the directed broadcast here, 100.255 for the 172.20.100 network. And we'll also see others, of course, as we progress through our Junos knowledge. Now, when a packet comes into the Junos operating system, it's going to take that packet and it's going to compare it against the entries that it has here in this forwarding table. Not the routing table, but the forwarding table. Remember, the forwarding table is a subset. It gets its information from routing tables. So it uses this table to determine the proper next hop. And that's important from a real world. It's important from an exam standpoint. Now, if the packet is actually destined to this local device, to this 2320 router, then the OS will process the packet locally. But what if it's sent to a remote device? Okay, if you have a valid entry for that remote device, it'll forward that packet out the next hop interface, associating it with the forwarding table entry. So, for example, you can see down here, there's 192.168.3.10/32. I'm going to send that out the gig E000 unit 0 interface. Now, it's also very important to remember that you might have multiple entries in your forwarding table that are matching a destination, and the device, my router, will use the most specific entry. In other words, the longest match of the prefix. Okay, the longest prefix match. And it uses the longest match always to determine the packet's next hop interface. Okay, I think we have a good idea of the routing table and the forwarding table that it generates. Let's talk about a very interesting concept and the ability to create routing instances. A very cool feature, and one that we're going to have to master as we move from our small enterprise Nugget Lab environment to larger scalable enterprise and service provider networks. Okay, so what if the router at the edge of Nugget Lab, let's say the customer edge we'll call it, is actually an enterprise router that is providing services in a metropolitan area for a wide variety of different business units. Let's say, for example, Nugget Lab is diversified into 2 or 3 different business units, and those business units are spread out over a wide metropolitan area, and you want to create networks over this man, separate routing networks for these different business units. Or what if you have a large campus and you break up your business divisions or your departments into different units, and you want to have them in their own routing domain so you can handle them or deal with them administratively in a different way? Or the most obvious example, what if Nugget Lab were a service provider with 2 to 10, let's say, customers, and you wanted to have a different routing instance or a different collection of routing tables and interfaces and parameters for your routing protocols, maybe different routing protocols for each customer, right? Maybe some of your customers use RIP version 2, some of your customers use OSPF, maybe even some of them use Cisco EIGRP. Border Gateway Protocol. How can we logically keep these sets of routing information separate from each other? Well, we can do this with routing instances. And this gives us a really flexible way to have kind of imitate or virtualize multiple layer 3 devices on a single router. Now, if I were to go and do the show route, let me move my cursor, interface instance, and let's do detail. Okay, show route instance detail. What we're going to see here is I've got a master instance. The master routing instance is the primary instance for all of the devices that are running Junos. And we can see that it includes, of course, the inet.0 routing table, which, as you know, has 11 routes, 9 which are active, 0 is in hold down, and 1 is hidden. We saw that earlier. Now, if I was using IPv6, my Junos software could generate other routing tables like the inet 6.0, and I could add those to this particular routing instance. Oh, by the way, look at the router ID. That's that loopback address we configured, remember? 192.168.1.1. There's other information down here. We can pretty much ignore this. This is all just basically for the kernel or for the operating system that it works with. We can just basically ignore that. Now, that being said, it's important to realize that multiple routing instances won't be covered on the JNCIA exam, and really the J-series router, especially the 2320 or 2350, aren't really great candidates for that anyway. You usually see that on some of the higher end platforms, but I wanted you to be aware of just some of the power where you could have your own customer routing instances where each customer could have their own inet.0 table, their own inet 6.0 table, their own interfaces, their own loopback interface with its own IP address, all those types of things. Even your own dynamic routing process or dynamic routing domain. Okay, we're about ready to jump into really our first practical lab of this JNCIA series, and our goal here is to get reachability between our 2320 router and our 2350 router, as well as reachability to this service provider router here. And so what we're going to do is we're going to create static routes, a static route between both of these two Juniper routers, and then a default route going up to the service provider. And we've already gone and configured all of our interfaces, including our loopback interface, so we're really ready to do that now. But here's the deal. Even though we created static routes, let's say between these two routers, and maybe we're using the loopback address of each one of these routers for reachability, or up to the service provider, when we go to try to ping the other devices, it's not going to work. okay? And it's not going to work because one of the most important routing essentials, and that is the context in which your Junos router is running under when it comes from the factory, okay? And this can be one of those troubleshooting things that you really pull your hair out, when you implement brand new routers. Now, if you were going into Nugget Lab, the routers are going to already be installed, and they can be in one of two different contexts. So let's talk about the secure context and the router context and how it would apply to our Juniper routers. Now, ever since about Junos operating system version or build, I think, 9.3 maybe, by default, when the router comes shipped from the factory, it's going to go through the initial startup and configuration, and the router is going to be placed in what's called a secure context. So really what happens is, out of the box, your router is pretty much hardened, okay? You've got a trusted zone and an untrusted zone, and the only interface that's in the trusted zone by default is gig E000. It's in the trusted zone for management functionality. All the other interfaces by default are in an untrusted zone. So right now, I can connect on gig E000 from my management station. I can ping on that interface to my management station, but that's it. Trying to get reachability on gig E001, 002, or 003 is only possible if I go through my zone configuration and, for example, place gigabit 002 into the trusted zone. And that is an option. However, that is something we're going to cover in greater detail in the security track, okay? So one of your options, if you're going to be using your routers and you want to allow all management traffic and all transit traffic, you want all of the interfaces to be bound to the trusted zone, or that what we call, actually, it's really technically the trust zone, is to basically enable this feature called routing context by loading a predefined template, which is JSR-series-router mode-factory.conf. And this is one of the things that's, kind of tricky about Juniper routers out of the box. It's kind of like, for you Cisco people, if I got a router, let's say an integrated services router from Cisco, and by default it had the zone-based policy firewall feature turned on all of the interfaces, and a policy was applied. It's kind of locked down. It's a stateful packet filtering firewall router by default. If you're familiar with the Cisco Adaptive Security Appliance, that's pretty much what the ASA is. The inside interface is basically trusted and everything else is untrusted. So that's the way Juniper routers come from the factory. I bring it up right now because this is really the perfect place to talk about it, because if I would have mentioned it 5 nuggets ago, you probably would have forgot about it, okay? Right now it's important because we have to understand, as we're trying to create these static routes to other devices and have reachability, this concept of the secure context and the router context is going to come into play. Now my 2350 is already in router context, and I can see this by going to the operational prompt and doing a show configuration command. And we can go down here, we can see, if we move down here to the security zones area, under security zones, it's going to say security zone trust interfaces all. That's one quick way to know that you're in router context as opposed to secure context. And you can see that the policy here for router context, the default policy, is to permit all. So I've routed over to 2320 now, my other router, and this is one that actually comes with the factory default. It's got the secure context enabled. And so let's take a look at the process of kind of converting this over into routed mode, so it'll be like my 2350. So check this out. If I want to do a show command, I'll do a run show security zones, and then we'll say trust. Show me the trusted zone. You can see that there's only one interface bound to the trusted zone, and that's gig E000 unit 0. This is the one that I'm actually telnetting into the device on. And you see me using Poderosa. Okay. Well, what I could do is I could change from secure context to router context. How would I do that? Well, the first thing I want to do is I want to do this command. I want to do a save config backup. So I'll take a copy of my configuration and back it up that way. So I've got that going for me. That's always a good thing to do. Then at the top level here, and you can always make sure you're at the top by doing top. I'm already there. I can load that router mode configuration file I showed you. So I would do load and then override, and then it would be the etc config JSR. Type this out. Now if I do this, I'm going to have to reset the root authentication on my device. I'll have to go back through all of my configuration of my gigabit 00 interface so I can access it from my management station. I have to enable telnet. I have to configure all my interfaces, loopback addresses, all of those things. Okay, let's go ahead and do some static routing, which is a very important skill to have. It's one that you might still use even if you're going to be using a dynamic routing protocol like OSPF, for example, and you can use it in combination with the dynamic routing protocol because remember, you can populate that routing table with routes from different sources, including static prefixes and dynamic prefixes. Now, what we're going to do here is this. We're going to first create a static route from 2320 here over to the loopback address on 2350, the address of 192.168.2.1. Now remember, the loopback address, it's really important that you use the loopback address as the address that represents that router. It doesn't really matter if you've got a handful of routers, but once you go to Nugget Lab and beyond, and you get into a large network with a bunch of routers, even hundreds of devices with dozens of links per router, well, trying to figure out which address you have to ping is going to be almost impossible. You want to basically hard code the identifier of the router as the loopback address, and you also want to make sure that your router always uses the loopback address as the source address in its IP packets. I'll show you that command as well. So the first thing we're going to do is we're going to create a static route to the loopback address, and the destination will be, of course, 172.20.66.2, this interface right here. So let's go over to 2320. Now at this point they're directly connected, right? So I should be able to ping, and I'll go ahead and ping the address of 2350, which we know is 172.20.66.2, and we'll use the rapid keyword on there. And there we go. 5 rapid echo request, echo reply. So that's a good thing. I also want to go ahead and create a default route to that upstream internet router that was in the diagram. Let me show you that again real quick. We'll have a default route, so by default our traffic won't be discarded. By default, anything that doesn't match in the routing table will go up to our gateway out to the internet, which is usually the way we're going to do this. So I want my default route to go to 172.18.1.1/30. Let's make sure I can ping that upstream router of the service provider, which, by the way, in this example is a Cisco 2921 Integrated Services Router Generation 2. So we'll do a ping, and it's going to be 172.18.1.1, and we'll do rapid keyword again, and very successful. Okay, awesome. And by the way, I can ping from the other devices to my 2320. Just trust me on that. I don't want to have to proof of concept that. As you can imagine, if I can ping one way and one way back, chances are I've got two-way reachability. So let's go ahead and I need to be in edit mode, right, to do our static route. Okay, I am in edit mode. Let's get into the edit routing options mode. That's where I want to be. So edit routing options. Remember, to get back to the top, just type in TOP, gets you back to the top, and there I am. So edit routing options. Let's be in that mode. Let's go ahead and clear the screen. Okay, so the command to set a static route is set static route. Pretty intuitive. And I'm going to put the destination. Okay, in this case, the destination network is really the loopback address of the 2350. So it's 192.168.2.1/32. Okay, and then we're going to say the next hop to get to that is basically the gigabit 002 interface of the 2350. Okay, basically that next hop over there, and we know that that is 172.20.66.2. And that's all we have to do. That's our static route. And of course, in this topology, if you're not going to be using dynamic routing, you would want to set static routes to the loopbacks of all of the routers. And you'd have to also go ahead and set static routes if you want to get to networks beyond those. So for example, if I wanted to be able to get down to networks behind this CR1 router or behind this CR2 router, or if there were other networks beyond, let's say on a gigabit 004 interface on the 2350, I would have to set static routes to those networks as well, and I could use as my next hop the loopback address if I wanted to. The great thing about a loopback address is it never goes down, right? It'll also come in very handy when we're configuring dynamic routing later on. Now there is one downside to using loopback addresses that way, I will tell you. One of the disadvantages is there's a tendency for, if you're using loopback addresses, to hide network outages, okay? If a network is unavailable and you're using loopback addresses primarily, especially with static routing, it may not be obvious to you, okay? And so we have some mechanisms we're going to learn as we get farther along in our progress, as we get prepared for Nugget Lab, to deal with having multiple connections and having different types of static routes. So if one static route goes down, we can, fail over to another static route, okay? And we'll look at some of those advanced techniques later on. Now remember from earlier that our INET4 routing table does have, by default out of the box, a default route that is going to be routed to the discard interface. That's the next hop, right? And it's there because by default you want the traffic to be black holed or dropped if it's not destined for some valid route that's in your routing table. However, we want to have a different type of default route, and that's going to go up to our service provider. So we're going to set this default route on J2320 up to the ISP in configuration mode by saying set static and route, and basically we're going to say 0.0.0.0/0. That's basically any, and the next hop is going to be, in our case, that upstream ISP router 172.18.1.1/30. Oops, we don't put the /30 on there. Okay, so the next hop is 172.18.1.1. That's the upstream router of the service provider, and there we go. I need to commit my changes. Let's go ahead and do a commit and quit so we can go back to operational mode and we can look at our routing table again. Now remember, we can do a show route protocol static. We just want to see the static routes. Now we can see here's our default route, 0000/0. It's a static route with a preference of 5 to the outside interface of the service provider on gig E003 unit 0. And here's our static route over to the neighbor router 2350 to its loopback address, and this is the outside interface on gigabit 02. Now here's the deal. I can't give away test questions, but let me tell you something. For the exam, I really want you to know that to create reachability between these two Juniper routers, I want to create a static route to the loopback address on 2350 with destination of this .2 address and configure that on this 2320. Then I want to create on the 2350 a static route to the loopback address over here 1.1 with the destination being gigabit 002 here, or 172.20.66.1. Okay, and as far as static routing goes, that's going to be the main hurdle you have for the JNCIA exam. Now at this point, I've created a couple of examples of static routes. A static route to a neighbor, to its loopback address, and a default route up here to my service provider, which is also a static route. And of course I could follow through on this, but I don't really have time to go to all the routers and do that. But if you know how to do a static route, then if you can do a static route going to one router, you can do it for all the other routers. And just remember that a default route, or a gateway of last resort, is just a static route where the destination network is 0.0.0.0/0. Okay, let me show you one other command here. All of the IP traffic that gets sourced from your router, as you know, is going to have a source address in the IP header in that source address field. And the address that's selected for packets will depend upon the interface that is used to reach the destination when you establish that connection. what you really want to do is you want to configure the router to use a fixed source address all the time. And the best way to do that is to use the loopback address as the source address. Again, it's much easier to keep track of your traffic, especially if you're using static routes and you have more than a handful of routers. So the way that we do that, and I want to do this on all my routers, but I'll show you the command here on the 2320, and that is the command to set the system default address selection. And that right there is going to make the loopback address the source address for all the packets, all the IP packets sent from this router and my other routers. Awesome. So make sure you remember those commands. Make sure you remember how to do the static route. Well, really everything I taught you in this nugget. All right, great job. Okay, before we finish up here and look at what we covered in this nugget, I do want to mention something about getting access to devices and practicing some of the things I showed you. Obviously, you're going to eventually want to get your hands on some equipment, get your hands on these operating systems on Junos, and be able to work through the labs that we're going to be doing in greater frequency throughout this nugget and beyond. Well, you could go out, if you wanted to go out to the internet, you can find plenty of articles on this, blogs about this. Go in and getting a copy of FreeBSD and getting Olive, O-L-I-V-E. You can also get GNS3 along with that, VMware Player, and you can create your own virtual environment. I'm not going to show you how to do that, okay? And let me tell you why. Juniper really doesn't support that. And they actually don't like you using Olive because it is, in a way, not using legal software. So here's the deal. Go out there and you can search for Olive. You can get copies of FreeBSD. You can use GNS3. There's plenty of YouTube videos that walk you through how to do that. You know how to use the internet. Just find your sources and you can create your own virtual environment. That, again, you definitely don't want to ever call tech support at Juniper and ask them to help you with your Olive installation, okay? That would be a bad idea. So because of that and because of kind of the gray area of legalities, I use real equipment with real registered operating systems and registered devices, okay? That's the way I roll, and that's the way I really want to keep things going forward here as a representative of CBT Nuggets. But there are solutions out there where you can go and you can, experiment. And you probably want to try to find a way to do that, or at the very least just go up maybe on eBay and find you a couple of, used Juniper devices. In this nugget, we looked at routing fundamentals. We looked at routing tables and instances, very important. We also talked about that very important concept of making sure that you're in the right mode, router mode versus secure mode, or router context instead of secure context. And of course, my devices are in the router context. We compared static routing to dynamic routing. We looked at some static routing connectivity, and I did ping between my devices. They're directly connected, so I was able to go ahead and make sure I had connectivity there. And of course, I can also ping after I've created my static routes. So now that we've got some of these essentials under our belt, in the next nugget, we're going to really talk about dynamic routing protocols, and I'm going to do it in a very, very unique and special way that I know you're going to appreciate, okay? So I hope this CBT Nugget was informative for you. I want to thank you for viewing.